I'm Melanie Quintana, a senior statistical scientist at Berry Consultants. At Berry Consultants, we design a wide range of clinical trials, most of which involve an individual subject being randomized to a single treatment or placebo and being followed over a period of time. However, there are situations in clinical trials where we want to allow individual subjects to receive multiple treatments. And that's what we're going to talk about today in this short video. Why we do this, when we do this, and some key considerations that we want to think about when we're doing it. In particular, I'm going to talk about two types of designs. The first is the one you probably think about most when you think about multiple treatments within the same subject, and that's a randomized controlled crossover design. The second is often called treatment switching to differentiate it from a randomized controlled crossover design. And it's when an individual is allowed to switch or cross over based on a period of progression or non-response. But let's start with randomized controlled crossover, a very simple, what's often called ABBA design. In these types of designs, each individual patient receives each treatment that's being studied. And the order in which they receive those treatments is normally randomized. Why we do this is so that every participant can serve as their own control, we can reduce variability, and we can increase power. Within these types of studies, a period in which you receive the treatment is called a period, and each period tends to be pre-specified in length, so say 6 months for each treatment, and those periods tend to be the same for each treatment. There could be 2 periods or 20, 30, up to 100 periods of different types of treatments given to a single individual. Between periods, we tend to have a washout period so that we can mitigate any carryover effects. These are effects of the first treatment that was given carrying over into the second period. Some key considerations that we want to think about in the randomized controlled crossover design are in fact this carryover effect. We want to make sure that the washout period itself is substantial enough to limit any effect that that treatment might have in the second period. Another thing that we want to think critically about is there a period or an order effect? So if you give a treatment in period 1, would we expect the effect of that to be different if it was given in period 2? Does it matter the order that the treatments were given? Oftentimes what we do to mitigate issues with this is we want to ensure that we have a disease that's chronic and stable so that the disease itself is constant over the entire trial. The final thing that we want to think about is the timing of the outcome itself. Oftentimes in a randomized controlled crossover study, we're thinking about short-term outcomes that are completely contained to each period. So for instance, change from baseline over the 6 months period. Under these ideal situations, so no carryover effect, no period effect, a nice short outcome that we can observe in each period, we can see a substantial increase in power between a crossover design and, say, a parallel design. Here in this plot, I'm showing the sample size needed for 80% power on the y-axis, and on the x-axis, I have the treatment effect itself that we're assuming. Here, these are standardized so that a 0.5 means 0.5 standardized unit different between treatment and control. If you look at the 0.5 standardized unit difference, you can see that we need a little bit less than 50 subjects for a crossover design compared to over 125 subjects for a parallel design. So crossover designs in this ideal situation allow us to get away with less than half of the same participants. Now, there can be some negatives to a crossover design. One is that every patient receives every treatment. So that means if we're thinking about a placebo-controlled trial, that every patient will be receiving a placebo for some period of time. And this may really not be ideal to subjects entering the trial. It may limit the subjects who want to enter. Another issue is that these types of trials could take longer in terms of the duration of the full trial because each treatment period is sequential instead of run in parallel. These are done many times in practice. This is just one example of a press release from Axsome Therapeutics. This was released in December. They ran a crossover design. They had two-week periods, and in between that, a 1-week washout. And this was a design to look at their efficacy of their drug in narcolepsy. And what they saw was a statistically significant reduction in cataplexy events or attacks in the treatment period compared to the placebo period. So now that we've talked about the randomized controlled crossover design, I want to switch gears a little bit to talk about another type of design often called treatment switching. And these designs come up when an individual switches or crosses over to another treatment after a period of non-response or progression. Oftentimes, these are one-way switching, so a switching from, say, placebo to active treatment, and these are done to address ethical issues and increase study participation, so that everybody knows that if there's a period of non-response or they're performing badly on placebo, they will receive an active therapy. Oftentimes, these are also done to actually learn what looks best both in first-line and second-line therapy. So instead of there just being a one-way switch where a subject goes from placebo to active therapy, there could be randomization post-progression to learn what all possible second-line therapies work best. Within treatment switching, you can start to see that things get a little bit more complicated than the nice randomized controlled crossover design. For one, the time of the periods could be very different, and they depend on when a subject progresses. So for each subject, they could be in period 1, say for 1 month, or another subject may come in and never go into period 2, stay in period 1 the entire time. Another issue is that a subject switches based on an intermediate outcome, not the final outcome that we're most interested in. So we're not able to observe the final outcome and have it be contained within each treatment period. So all of the same considerations from randomized controlled crossover studies still hold with treatment switching, but we also want to account for when we switched and what treatments we switched to in the primary analysis. Because switching on this intermediate outcome before we observe the final outcome may actually dilute the overall treatment effect that we are able to observe. Imagine if everyone on placebo switches over to the active treatment after a month, then those two groups are probably going to end up looking pretty similar. So we need to be very careful and adjust for different effects of this switching. We need to be able to adjust for any potential carryover effect from the first line treatment to the second line. We need to be able to understand if a treatment is different in the first line versus the second line. Is that effect different? And then we need to take into consideration the amount of time that each patient is in each period. Now, treatment switching is done many times in oncology. This is just one example of when it's done in practice. This is the Precision Promise Pancreatic Cancer Platform Trial. And this is a trial that's a perpetual trial that's interested in looking at many therapies over the course of time and which ones help pancreatic cancer. In this trial, we have adaptive randomization to receive a first-line therapy. And then, if an individual progresses, there's adaptive re-randomization to the best performing second-line therapy. This trial is meant to understand which therapies work best in first line, as well as which work best in second line, and what are the sequence of therapies that work best. And the statistical analyses themselves allow differential effects in the first and second line therapies. So now that we've talked about two main types of designs with multiple treatments, I just want to acknowledge that there are many more designs that involve multiple treatments. One that's gaining popularity is a dynamic treatment regimen, or what people are calling a SMART design. And this also involves re-randomization to subsequent treatments based on intermediate outcomes. And also, we're interested in learning what is the best and most ideal sequence of therapies. And finally, where this is coming up is also in perpetual or platform trials. So platform trials themselves are meant to be these freestanding arenas where drugs come in and are tested, and then they come out to see which ones are the most effective within a certain disease. And what we're seeing happen in these platform trials is that after your initial period of enrollment and serving to test for a single regimen, a subject may still, after they're finished with that period, be able to re-enroll in the trial and have a repeat randomization. And we need to take into consideration this repeat randomization. In summary, I hope you've seen today that there are many valid reasons for allowing an individual subject to receive multiple treatments over the course of a clinical trial. For increase in power, for ethical reasons, and also to purely understand which sequence of treatments work best. Across the board, when we're dealing with a trial of this nature, we need to make sure we clearly document and report the multiple treatments that each subject receives, so that the statistical analyses themselves can carefully consider the impact that these multiple treatments have on the final endpoint. Thank you all for watching this short video today. I hope you learned a little bit something more about multiple treatments within the same subject, and please go to our website to watch some more of these videos.